let's get started here. So test number 3 is on Wednesday, so we will spend the last portion of class reviewing for the exam. All of you should have received your project number 3s back. As I said, they were quite good. Excuse me. And because I don't really have any further comments other than what was posted on the listserv. Are there any questions about project number 3? Okay. Are there any questions overall before we get going here? Okay, so we have been talking about logistic regression now over the last few class periods. We're using logistic regression to classify an observation into one of two possible populations. And the way that logistic regression is typically represented is that we have a response variable, a y, and it can be either a 1, which is often referred to as a success, or it can be equal to a 0, which is often referred to as a failure. So we have two different populations denoted by a 1 or a 0, or a success or a failure. That's just standard terminology used with logistic regression models. Well, once we take a sample and we estimate the parameters in our model for the sample, what we're able to do then is come up with estimates for the probability of success, which we denote by pi hat. And we compare this pi hat for a particular observation of interest to a cutoff probability. So for example, maybe the cutoff probability is 0.5. If pi hat is greater than 0.5, then we classify that observation, or we predict for that observation that the true population that it comes from should be y equal 1. If instead it is less than 0.5, then we predict a y equal to 0 for that population. So that's how we make the predictions, or you could say the classifications. Quite simple. Now, of course, we don't necessarily need to use 0.5 for that cutoff probability. And we looked at a tool called a ROC Curve last time to help us make a judgment of, should we to make judgment of what should we use for a cutoff probability. What the ROC curve looks like then is as follows. We have the sensitivity of a classification method on the y-axis. And essentially what that is the estimated probability that you classify an observation as a success, given that it is actually or truly a success. In the notes I had originally phrased a success, we talked about this in terms of HIV testing. A success, I guess in that case, would be HIV positive, corresponding to the terminology I'm using here. And then on the y-axis, then we used, the x-axis, we had 1 minus the specificity. Which also essentially is a false positive rate. I should say essentially it is. And what that means is the estimated probability that you classify as a success, given it is actually a failure. So that's what's on our axes for a ROC curve. To actually then get the ROC curve, what we do is we look at a whole bunch of cutoff probabilities. Let's say 0.1, 0.2, 0.3, all the way up to maybe 0.9 perhaps. And for every single cutoff probability that you look at, you calculate the sensitivity, you calculate the 1 minus specificity. So that in the end you might have something that looks like this if you were to plot then the corresponding points for each of the cutoff probabilities. We also put a numerical scale here. And then what you can do is just simply connect the points. Well, I try to. And if you connect the points correctly there, you got your ROC curve. So we had an example of an ROC curve on page 26 of the notes. This was for the place-kicking data set. And so with this ROC curve, what this essentially means is this, that if I want to have a sensitivity of 0.9 for a classification method, then that means my corresponding 1 minus specificity, or in other words, the false positive rate, will be about 0.55. And there is a particular cutoff probability that you can find that gives you that, essentially that point on that plot. Well, how do you find that particular cutoff probability? Unfortunately, it's not necessarily the easiest thing to do with these ROC curves the way that they're implemented in R. And actually, I've never seen it easy in any software package. But this is how we can do it. So this is now new stuff. Okay. Now I guess actually we'll review a little bit more first. So to review how this ROC curve was created, remember we use functions in the ROCR package. And then it's the three-step process. First of all, you need to use the prediction function from the ROCR package. And what this does, or what you do, first of all, is you pass in your pi hats for all your observations in your original data set. Also, you pass in the true classifications of your observations. And then with the prediction function, what that does, it calculates for a whole bunch of different cutoff probabilities how many observations will be essentially classified as a success, how many will be classified as a failure. I put the results into save.pred. Then, step 2 of the process, I use the performance function, which allows me to calculate various accuracy measures, in this case the sensitivity and the false positive rate, and 1 minus specificity. And I also pass in the results from the prediction function as well. And then lastly, the third step is that you simply plot the results from the performance function. And what you get then, where is it? There it is. There's my ROC curve. Okay. Now with that, then let's look at how we can find a particular cutoff rate. In particular, what I would like to do is find a cutoff rate for a specificity of 0.5, which would be then also 1 minus specificity of 0.5. Perhaps that's what I feel as though that I can deal with for this particular instance, a false positive rate of 0.5. I'm going to find the corresponding sensitivity and then also the corresponding cutoff probability. Okay, so this is the process. First of all, to make it a little bit easier in terms of syntax, I'm going to extract all the values that were plotted on my x-axis of that plot. So save.perf at x.values is all my x-axis values that are on my plot. Notice here that we have this bracket, bracket 1, end bracket, end bracket. Well, these x values here are stored as a list inside of this this object, but it's a little bit of a different list than what we've seen before with the GLM function. In particular, the components of the list are not actually named, and so the first component then is just given by default in R, a bracket, bracket 1, end bracket, end bracket. So then to extract then the corresponding x values, I use that then corresponding syntax. I put that into an object called 1 minus dot SPEC for specificity. All my y-axis values, my sensitivities, are stored in y.values of save.perform or save.perf. And I extract them in the same way, put that into an object called sense. Let's go ahead and run that code. then the corresponding cutoff probabilities happen to be stored in an object called alpha.value, so save.perf. So I can put that in there. Then what I want to do is actually create basically a true-false indicator for whether or not my specificity is close to 0.5 or not. So the first thing I do is I look at 1 dot minus dot spec greater than 0.495. So what does that do? What does that return if I just execute that part of code? It gives me what back? Trues and falses. So trues and falses corresponding to if my specificity is greater than 0.5. And then also I look at the same thing for, greater than 0.495. I look at the same thing for 0.505, but now less than that. And then I want to combine those, so I'm looking at essentially a range. That will be right around 0.5. So to combine the two, I simply use an ampersand. That means and in R. So that when I execute that code and put it in an object called CK for check, you can see that we only get a few truths. So these are the corresponding, let's say, elements of my sensitivities, my specificities, and also my cutoff probabilities that correspond to the my specificities that I'm actually interested in. So simply, I take my sensitivities, I work with all those trues and falses, same thing for my specificities, same thing for the cutoff probabilities, and finally, we get what we needed. So, again, if I wanted a 1 specificity of 0.5, notice I don't get it exactly, but I do get two things that are very close. So what this says is if I want a 1 specificity of 0.5, I should choose a cutoff probability about 0.71. And that gives me then a corresponding sensitivity about 0.91. Yes, it is kind of a long process. You would think that it would be a little bit easier to do. What you could do is actually write your own function to make it easier. But those are the steps that you need to implement inside your own function to do it. Any questions? Okay. Now there are also some nice tools or nice little options with the ROCR package that you can do that does make it a little bit easier in terms of getting these, at least approximating what the cutoff probabilities would be. And this is shown on page 29, the corresponding plot. What I can do when I implement the plot function, just like what we did earlier, I can add two additional arguments. First of all, there's an argument called print.cutoffs.at, where you can say, I want actually put on the plot where the cutoff probabilities would be on that curve. And I'm going to take a sequence of numbers from 0.3 to 0.95, 0.1. And also I'm going to add some nice little color to the plot as well, so that when I execute it, let me actually just go on over here to Word. Here's my plot. So first of all, you see some numbers plotted on the curve. If you notice, there's like an open plotting point here. That shows then where exactly the 0.9 cutoff probability would be. So for a sensitivity of about 0.7 and a 1 specificity of about 0.18, the cutoff probability is 0.9. So that's a nice little option there. Also, then we have with that the colorize argument, that's what produced this part right here, along with then the curve being colored. So, for example, higher cutoff probabilities are closer to red in this scale. So we can see that these are my higher cutoff probabilities. And then as you get farther and farther away from red and get closer to blue, you can see my cutoff probabilities decrease. And you can see how that's illustrated by the color of that curve. Yeah, it's a nice little thing to have there. Now you can also do other kinds of plots too. Excuse me. Hold on, let me make sure I'm not getting ahead of myself here. On page 29, top of page 30, I also do a plot, an ROC curve for the validation data. You can take a look at that code on your own. And then lastly, what I was trying to get at is that you can use the functions from the ROC-R package to do other kinds of plots too. In particular, what I have here is a plot of the sensitivity versus the cutoff probabilities here. So you can see as my cutoff probability increases, my sensitivity goes down. You should think about intuitively why that should happen. Please take a look at the corresponding code too on your own. Okay. Now, both with discriminant analysis and also nearest neighbor classification, a way to look at how these methods were working in terms of classifying these observations, we would run a principal component analysis, and we would then use we would plot the principal component scores, and we would color the corresponding plotting points by the actual classifications themselves. So just to review a little bit here, for discriminant analysis, this is what we got. This is for linear discriminant analysis, that is. This is a plot of the first two principal component scores. And we can see how and this is the actual notes that I had made on the plot previously. You can see how, we have this, pretty definite dividing line between the successes and the failures in our classification. And then when we came over here to nearest neighbor classification, unfortunately I got off my page here, we can see how the blacks and the reds were somewhat mixed. So we no longer have that straight line there that we have with discriminant analysis. Let's see what happens now with logistic regression. So I'm not going to go through the code because the code's basically the same as we've seen before. And if I were to use a cutoff probability of 0.5, this is what we get. Perhaps it's a little bit harder to see up there, at least when I'm looking at it, it's a little bit harder to see. But you can see, the blacks, there's a lot less blacks in this plot than there were before. But also you can see that the blacks are a little bit dispersed amongst the reds in comparison to what we saw with discriminant analysis, but less so than what we saw with nearest neighbor classification. So again, that's, in case I didn't say it, that's for a cutoff probability of 0.5. If I use a cutoff probability of 0.7, this is what I get. You can see how this looks now a little bit closer to what we saw with linear discriminant analysis. But we do see, to some respect, the blacks a little bit more interdispersed amongst the reds than what we saw with discriminant analysis. But definitely not as much as we saw with nearest neighbor classification. Okay, are there any questions? So with respect to material that you're responsible for test number 3, this ends the material for test number 3. We are not done with this section, but this ends the material that you're responsible for test number 3. Okay, so now that takes us to page 35. There are going to be particular situations where you're not for sure which, let's say, logistic regression model to use to classify your observations. And so how do you make then a choice between the different classification methods? We've talked about this a little bit before. Let's just talk about it again, but in a little bit more detail. So again, here's my my ROC curve. I have sensitivity versus 1 minus the specificity. Put numerical scales on this. And so what you can do then is, let's say you have two different logistic regression models you're trying to choose from. What you can do then is plot ROC curves for both models. So that's, let's say, for one model. Let's do another model here as well. So in this particular case, which model do you think is better? The red one, or the one that produced the red curve, or the black one? The red. Because you always will have a higher sensitivity and lower 1 minus specificity with the red than you would with the black. Okay? So that's not too difficult. But let's say instead you had something that looked like this instead. Now which would you choose? Well, now it's not necessarily a clear-cut case between the two. And instead, here are some options. If you were really concerned about, let's say, the false positive rate, the 1 minus specificity, if you're really concerned about that, you want to minimize the false positives, then you might be thinking the red would be better, because for lower values of the 1 minus specificity, the red is higher than the black. Alternatively, if you needed something that was very sensitive, and you were not as concerned about false positives, you would probably choose the black in this case, because the black is higher than the red for very large sensitivities. So that's how you can make a judgment. If instead, let's say that you were not necessarily as concerned about sensitivity and false positive rate, you want to know overall, let's say, which of these methods are going to be better, instead there's another way that you can approach this. You can look at the area underneath these curves. We talked about this briefly before. Let me just throw up a third curve up here just to emphasize. So this third curve, which is in blue, obviously is better than the other ones. Note that your sensitivities can't be greater than 1. It's just I can't draw very well. But if you look at that blue curve there, you can see that that has a higher area underneath of it than the other two curves. So this one would be better. And as we discussed before, the closer that this curve, or more, the more, let's say, more bowed shape, that curve is towards that up here, this corner, the better the method, and thus the higher the area underneath the curve will be. So when you're left in a situation where you're trying to decide between two different methods and the lines cross there, what you could do is look at the area underneath the curves. The method that has the higher area would correspond to the better, using that criteria. Okay, so let's take a look at this now, all of this in the context of the place kicking example. Okay, excuse me. First of all, to calculate the area underneath the curve. If you remember when we looked at the performance function a few minutes ago, what we had previously put in there was two options: sense for sensitivity, and also FPR for false positive rate, or 1 minus specificity. Instead, what you can do is put in there AUC for area underneath the curve. So with the model that we've been talking about before, the area underneath that curve then is shown down here to be 0.85. Now, how did I know that that was where the area underneath the curve was? Well, there happens to be a slot called y.name, and it's called area underneath the curve. So that's why I knew for y values, that's what that represented. It could be labeled better, but that's just the way that this function works. For the validation data set, we get an area underneath the curve that's just a little bit lower, about 0.839. Now let's look at a situation where you have two different models to choose from. And let's say that I'm looking at a situation where one of my models has just distance in it, so none of the other variables, only distance. So what I could do is I could estimate my model using GLM as we've done before. I get my pi hats as we've done before as well. put the results into pi dot hat dot dist, and then I can go through the same process, use the prediction function, use the performance function, and then what I will show you shortly, I'm going to use the plot function to actually plot the ROC curve for this particular model. Let's compare that model then to a model that only has elapsed 30 in it. Remember what that represents is the minutes left to go in a half when the place kick is attempted. You would think that the lower the number, meaning lower the minutes, the more pressure perhaps would be on the place kicker because it's getting towards the end of a half, perhaps. Notice when I estimate the model then, I get a p-value of 0.0177 for a lap 30. So there is some evidence, it's not necessarily very strong, but there is some evidence that lap 30 is important in predicting the probability of success. And I failed to mention this before. With distance, we have an extremely small p-value. R elicits at 0. It's not actually 0, it's just something very, very close to 0. So again, I can do all my predictions, get all my pi hats out, use the prediction function, use the performance function, and then we could do some plotting of ROC curves. So here is the code for the plot that we're going to see shortly. First of all, I'm going to do a plot for my original model that had all the variables in it. On top of that, I'm going to do a plot then that just is for the model for distance, an ROC curve. And the way that I'm going to plot this on the previous plot, I add the option or argument, add equal true. I'm going to do the exact same thing then for the lap 30 variable and its corresponding model, add equal true again, and put a nice little legend on it so we can see what's going on. And here is the corresponding plot. So what's the worst model? The model that has just a lap 30 in it. You can see then the black and the red models there. The model that has all the variables versus the model that has just distance itself. They're very, very similar. So in fact, generally speaking, you can do just as well with only having distance in your model. That's kind of interesting. The main thing that changes a little bit is those cutoff probabilities. We could look at then the corresponding area underneath the curves using the same mechanisms as we've done before. For all the variables, resubstitutions 0.847. For using distance 0.838. So it is a little bit less. But again, these numbers are quite close to one another. So there's, in a practical sense, there's probably not a whole lot of difference. And then looking for your lap 30, 0.56. A lot less. Indicating, of course, it is worse. If you remember last time, we talked about a line of chance. This is where the line of chance would be. And essentially, we said that in order for an ROC curve or in order for a classification method to have any use at all, we need the ROC curve to be above that line of chance. Well, we can see with the lap 30, it's only barely above. What would be the area underneath the line of chance? 0.5. So you can see 0.5 was kind of close to 0.56 for the lap 30 model. Also, this example helps to point out that just because a variable is, let's say, significant, as the lap 30 to some respect was, depending upon what your level, your alpha was that you set, you can see that just because a variable is significant does not necessarily mean it's going to be very helpful for classification. Classification, in other words, predicting success versus failure, is something quite different from whether if a particular variable actually, let's say, affects the probability of success. Okay. Are there any questions? Okay, next, page 40. Now, unfortunately, one does not always get model convergence when you estimate these models. Again, what I mean by that is that we're using an iterative numerical procedure to estimate the betas in our model. And what can happen is that these estimates of these betas can continue to change throughout the iterative numerical procedure, and they never quit changing. By default, R uses 25 iterations with the GLM function. You can increase the number of iterations if you want to by using the max-it procedure. And that's, generally speaking, the first thing you should do if you don't get model convergence. How do you know if you don't get model convergence? Well, you'll have an error message coming back to you with the GLM function. Now, the most common reason for not getting model convergence is something called complete separation. And due to time considerations, I decided not to cover it in this class. I do strongly recommend that you read this over. You will not be tested over it, though. I do strongly recommend that you read this over. If you want a more, let's say, detailed explanation of it, please take my Stat 75 class, where we do talk about logistic regression in a lot more detail than what we do here. But complete separation can be a problem, but it also could be a good thing too. What complete separation basically means, just to real briefly to tell you about it, take a look at the plot on the left. Suppose you have a situation where you have just one variable called x1. You want to estimate the probability of success. And what I've done is plotted the actual data. That's what's represented by the open plotting points, those black plotting points here. And what we can see here is I have 5 observations that have a y equals 0. I have 5 observations that have a y equal 1. And you can see that x basically perfectly separates out the y equals 0s and the y equal 1s. So you can see that, in fact, you can get a perfect 100% classification if you think of resubstitution here by simply saying all the low x's, y equals 0. All the high x's, y equal 1. The problem, so that's good, but the problem is you're not going to be able to get a model using regular old logistic regression. Because you can see this I plotted what the model is at, let's say, the last iteration. You can see that the slope of that line where I circled it is essentially infinity. And that's the problem. So it's both good and bad complete separation. What can be more difficult than, so you can see that this is obviously easy to see. What can be more difficult though is, let's say if you don't have just only one independent variable. Suppose you have 10. You can't do a plot like this to see if you have complete separation or not. So anyway, please take a look at this section on your own. That just gives you a brief explanation of what it is. And also I do discuss 2 things that you can do if you have complete separation and you still want to get a logistic regression model. So that takes us then to page 45. So just to sum up then this section, some additional notes. So there's a lot of research done on ROC curves. If you go to an actual statistical conference like the joint statistical meetings, you will see sessions dedicated to ROC curves. And because of that, there's been a lot of other development done in terms of packages. In particular, 2 other packages that you can use to do ROC curves are those 2 there. You can take a look at those if you're interested, but you're not responsible for it. What about variable selection? We talked about variable selection with respect to discriminant analysis. We talked about variable selection with respect to nearest neighbor classification. We said there's not a good thing to do. Well, there are standard ways to select variables in a logistic regression setting. If you've taken a Stat 870 course, you know of many different methods for regular regression models. Those methods, generally speaking, can be applied here as well. The problem, though, is it doesn't actually measure classification accuracy. And if that's what you're really interested in, that's what we are in this class, it isn't getting at your central question about which variables allow me to classify the observations with the highest accuracy. So it still is not getting at what you really want. I do a lot of my research deals with looking at sensitivities, specificities, and also two other accuracy measures that I think it's important to at least bring up to alert you that there are other ways to measure accuracy that are often very important. The two most important ones that are typically presented, especially just in a class like this, are sensitivity and specificity. But there are two other very important ones. One is called the positive predicted value, PPV, and another one's called the negative predictive value, often abbreviated with NPV. And in the context of our HIV example that we were looking at, remember we had a new, let's say, HIV test that we wanted to use, and that test gives you a positive or negative result. But we do also have, let's say, a gold standard method out there that gives you what you could treat as a true positive, a true negative. And what we can do is look at accuracy this way. So the PPV is the estimated probability that someone is actually positive, given that they were classified as positive. Notice how this is essentially kind of changing the order of the stuff that's in here in comparison to sensitivity. If you remember, the sensitivity was exactly the same, except for we put classified positive there, and we put actual positive there. So now we're just kind of looking at things from a different point of view. The negative predicted value then is estimated probability actual negative given classified as negative. So you can see that we're just simply flipping these two things here in this specificity definition. Well, why are these important? Here's why. I think this is, excuse me, I think this is a good example. Let's say that you're being tested for some kind of, let's say maybe an infectious disease. And so the doctors had some lab work done on you and gives you a call or comes into whatever room you're sitting in, comes in with then the results of these lab tests. And the doctor says, I'm sorry, but you have tested positive. Now, what should be the very first thing that you should say to your doctor or ask your doctor? It should be, doctor, what's the PPV on that test? Well, why? So you have been classified as positive. If it was HIV, you have an HIV positive test. The first thing that you would want to know then is what's the probability that you are truly positive. So that's why these kinds of measures are important. Again, sensitivities and specificities are typically thought of as the most important when evaluating, let's say, diagnostic tests or other situations. You'll see those most quoted. But PPV and NPV are very important too. I didn't really think of it as that important until a number of years ago when I was in some of my research. My statistical research, an application of it is often used for testing people for chlamydia and gonorrhea. And some of the people that were involved in this research were at the UNMC. And I had written up some stuff showing how fabulous my research was for them to see if they wanted to apply my research. And I really was focusing on sensitivity and specificity of this diagnostic measure that I came up with. And while they were interested in that too, what they were even more interested in was the PPV. And so that got me thinking more about, definitely that is important. And put yourself in the shoe of, let's say, someone who has been diagnosed with the disease. What would you want to know? Okay. So lastly, then, so when you're done trying, typically in a situation, yes.
We have to make sure that the doctor uses the logistic regression.
You can still calculate these measures, sensitivity, specificity, obviously, because we've always looked at these classification tables. You can still calculate those for discriminant analysis or nearest neighbor classification. Do the same thing with PPV and NPV. The advantage of using logistic regression, though, is that you can change the cutoff probability. And so if you were really wanting to have a very sensitive test, you could change that cutoff probability to make it a very sensitive test. With nearest neighbor classification, discriminant analysis, you don't have as much flexibility. Does that answer your question? Okay. Now, typically in situations where you are trying to come up with, you're trying to classify observations into one population or another, you are going to apply a bunch of different statistical methods, such as discriminant analysis. And we saw a variety of different types of discriminant analysis, such as nearest neighbor classification. We saw different, different values of K you could use with that. You could use logistic regression with different cutoff probabilities. There's many other classification methods out there, like one called classification trees, another one called random forest. There's tons of classification methods out there. You could dedicate a whole class to classification itself. But typically in actual application, you're trying a whole bunch of different methods. And you need some way then to summarize the result that you get back. And what I recommend that you always do is do a plot such as this. This, of course, is a trellis plot that we saw back in the graphics section. My actual code to construct this plot is in plot_accuracy.r. Please look at that on your own. And so with a variety of methods that we've tried with the place-kicking data set itself, I've simply summarized the specificity, the sensitivity, and the overall accuracy. So for example, with a cutoff probability of 0.7, here's my accuracy right here. It's about 0.86 or so. When I use a cutoff probability of 0.5, I get a little bit more in my overall accuracy. With nearest neighbor, with K nearest neighbor, if I use K equal 4, I get an overall accuracy of about 0.85 as well. And so you can see an overall measure of, or overall summary of how well your methods have done. And especially if sensitivity or specificity are very much of interest to you, you can then weigh your sensitivity versus specificity by looking at those other parts of the plot. I first did one of these plots actually when I was working on that Sunny D juice container problem that I told you about. And I've always done these plots ever since whenever I had a classification problem, because it helps you make judgments about which ones you want to use. Okay, so that concludes the logistic regression section. Are there any questions? Rather than getting into a whole new section right now, why don't we start reviewing for the exam? So I mentioned a few weeks ago that I'm using a new computer here. This is a Microsoft Surface Pro 2. So far, it's worked out pretty good. But I've used tablet PCs now for 10 years, and there are a few small things that I don't like about it, or I like better with a regular old tablet PC. And that is, I don't know if you've ever seen the various promotions for these surfaces. I have this little hinge here that allows me to rest my monitor on, and with the original Surface, you only had one choice for a hinge, if you can see this here. Now with the new Surface, you have two choices that you can use. And so that was like a big thing that they did with these surfaces. But as one review said, well, why don't they allow you to have as many as you want? And what I have found that writing in a classroom situation like this, I really want to basically go like, I need to make it a little bit at this angle so I can write better. And I have problems writing because I don't have the right angle. Anyway, just a little bit of a side note. So if my writing here today is poor, blame Microsoft. Okay, so this is test number 3 here. Again, of course, we'll start at 9 a.m. You can go till 10:25 if you like the extra 10 minutes to finish the exam. Please note, on this exam, at least the way it's written right now, I might make small changes as before Wednesday, but the way it's written now, you will need to install a package on your computer at some point during the exam. Okay? Now, given the material that we have covered, you should have a pretty good idea of probably what package you would need to install. I'm not going to tell you. But you should have a pretty good idea of what package you would need to install. Before the semester started, I had these computers, updated with the packages to try to avoid a situation where you would have to actually install a package during an exam. But the problem was I was, this was back in probably July. I was trying to predict what I would need in terms of packages in terms of November and December. And given that I hadn't used R fully for this course before, it was kind of difficult to make that prediction. Okay, so again, there's going to be a formula sheet. It is available on my graded materials webpage on my course website. You will have access to that, to the PDF, during the exam. If you haven't already taken a look at it, I strongly recommend that you do. The material on the exam starts with cluster analysis. It does discriminant analysis, nearest neighbor classification, and also logistic regression up to the point that I mentioned to you today. So it's not the entire stuff that we talked about today. The test itself, the way it stands, of course there's 100 points. Problem number 1 is on cluster analysis. It's worth 28 points. I'm going to give you a data set, and you need to do some cluster analysis with it. Problem number 2 is 27 points. And it's going to be, you're going to need to use a classification method, meaning it's going to be over discriminant analysis, nearest neighbor classification, or logistic regression. Problem number 3 is 23 points. And you're going to have to use now a different classification method. And lastly, number 4 is 22 points. There are 3 short answer questions that are not necessarily connected in any way, similar format to what you've seen in the past. I guess also I should mention there is a number 5 that is 3 points extra credit, which I'm sure all of you will be able to get. Structure of the test, same as before. You're going to use the computers that are in front of you to help answer questions. You'll have access to R. You'll have access to all my R programs available on my course website. You cannot access my notes, though. You cannot access answer keys to past projects. You cannot access homework that's located on my website either. You cannot communicate with others in the class. So, same structure as before. Please remember to always, of course, put your answer on the written or on the paper copy of the test, but please remember to always show your answer. Okay? We've talked about a variety of different ways that you can show your answer. Put the corresponding equation that's needed to do something. Maybe also put some stuff involving our code as well. But you need to show your answer. Let's see. Okay, let's talk about. Let's review the material itself. Okay, so cluster analysis. Maybe if I tried this, that might work. Okay, so cluster analysis. Understand the hierarchy in terms of the various methods for cluster analysis. So if I had cluster analysis here, there are 3 different ways to do cluster analysis. There's hierarchical, there's non-hierarchical, and then there are what are called model-based approaches. We did not do model-based approaches in our class. Under hierarchical, there are agglomerative and divisive. Know what a divisive method is versus agglomerative, but we did not do divisive. So just understand what it basically is. With non-hierarchical, there's, for example, k-means clustering. There's k-medians clustering. There's other methods, but we just focused on k-means. Then under agglomerative, we looked at a whole bunch of different ways to do that. We looked at nearest neighbor. We looked at farthest neighbor. We looked at Ward's method. We looked at the average method. And we looked at the centroid method. Make sure you understand those particular methods. I think a great example that I had in the notes was showing you how you could do these methods by hand without R. Make sure you're familiar with that example that I gave in the notes and that you could actually do it for another example. Same thing even with k-means clustering too. Make sure you understand how you could do it by hand for a very, very small data set. Obviously, make sure you know how to implement these statistical procedures in R. Advantages and disadvantages of the various procedures too. For example, with nearest neighbor, you often have what's called a chaining effect occur, where you're having elongated clusters, and depending upon that situation, that may or may not be desirable. A big thing that we spent a lot of time on was determining how many clusters should we use. And this is not necessarily a definite answer. You could have multiple answers that are correct, but of course you need to use them the correct justification for what you chose. There are some wrong answers though too. When choosing how many clusters, when we did agglomerative, we had then the hierarchical tree diagram. And that was the primary tool that we use. make sure you understand how to use a hierarchical tree diagram to make a judgment of where to cut the tree, let's say, and choose a particular number of clusters. We also looked at ways that you can determine what are good and bad clusters. And then this often then gets into other graphical measures to decide on the number of clusters. Where if you only have two variables, well, you could easily do a nice simple scatter plot. But if you have more than two, definitely more than three, you could use, for example, principal component analysis and look at the principal plots of the principal component scores, 2 dimensions or 3 dimensions, to make a judgment of, well, which clusters are, or does my clustering process make sense in terms of the clusters that were chosen? Or do I have some maybe potentially bad clusters formed? Oops. Then with respect to k-means clustering, we looked at this measure called W to help us decide, well, how many clusters should we use? And W has some similarities to what you've seen in ANOVA, where you had within sums of squares that you were looking at. And essentially, W is within sums of squares divided by total sums of squares. And essentially what you're doing is if you remember, we had a plot that looked like this. And you could plot for every number of clusters, you could plot W. And what you're doing is you're essentially looking for where does the plot start leveling off. And where it starts leveling off, that shows you now that you're not really gaining much by increasing the number of clusters. So I might pick, for example, a number of clusters that corresponds to this point right here. With k-means clustering, we had something that we need to do at the very beginning called forming cluster seeds. If you remember, observations are randomly chosen from your data set for the initial cluster seeds in which allow you then to grow your clusters. And because that they're chosen at random then, you have to be concerned about, well, would you get the same answer if you choose different initial cluster seeds? And so because of that, you need to rerun your k-means clustering multiple times to make sure that you do, in fact, get the best results in the end, in terms of a lower W. Okay. So that's cluster analysis. Then for discriminant analysis, we looked at two main methods, linear discriminant analysis and quadratic discriminant analysis. Make sure you know the difference between the two. With these methods, then, we have to worry about these things called priors. Typically, you set them to be proportional to the number of observations that come from every population in your data set. With linear discriminant analysis itself, with equal priors, we looked at 4 different discrimination rules. You remember, we started off with the likelihood rule, we went to the linear discriminant rule, we went to Mahalanobis distance, and then we went to posterior probabilities. Make sure you're familiar with all 4. If I ask you to do something, let's say, by hand on a test, using those without using the LDA function or the QDA function, make sure you know how to do that. Okay. We also looked at 4 different accuracy measures. The best, go out and collect some new data. Of course, there are disadvantages to doing that. You could also have a holdout data set or a validation data set. You could do cross-validation. You could do resubstitution. Make sure you know the advantages and disadvantages of all of them and how to actually implement them. Not just in discriminant analysis, but also for nearest neighbor classification and logistic regression. We also spent some time with principal component score plots. The reason being is because we wanted to, typically if you have more than 3 variables, and you want to get some idea of how this discriminant analysis method is working, you can do these plots to see which observations are being classified correctly or which are being classified incorrectly, and gives you an idea of maybe where your method is having problems. You can also do parallel coordinates plots as well as a way to examine your method that you are implementing. If you remember, we can look at these plots too before you even do the discriminant analysis, get a general idea of, am I going to have some kind of success at all? Make sure you know how to interpret them, those plots in those situations. So then that takes us then to nearest neighbor classification, a relatively short section. The method is very simple. You're just simply looking at what are your nearest neighbors to a particular observation of interest to determine how you should classify that observation into what population. The thing that's the most difficult to deal with is then how do you deal with the ties that you may have. So if you have k equal 2, if you have one observation for population 1 and observation for population number 2, how do you settle the tie? Make sure you understand the advantages and disadvantages of using nearest neighbor classification versus discriminant analysis. There's a few. Obviously, how to implement this R, how to actually do it by hand if I ask you to do it, rather than using R. Also, how do you choose K? Well, there's not necessarily a good way to do it other than just try a whole bunch of Ks and look at which gives you the best accuracy overall. And again, you can use principal component score plots. You can use parallel coordinate plots to get an idea of, well, how your method is working, where it's having problems, or where is it doing good. Then lastly, that takes us to logistic regression. The easiest question that I can give you on this test is to ask you to estimate a model for a particular data set. But make sure you know how to correctly state the model. So, there's a variety of different ways to state it. Of course, all of them require a pi hat in them. If you only put a pi when you're stating the model, you will have points deducted, unfortunately. There's a difference between pi and pi hat. Then, how would you then estimate pi? Well, you simply put in your x's into your model, your estimated model that is, and do the math. You get a pi hat out. Once you get the pi hat out, how do you make a decision about, do I classify this observation as a success, or do I classify it as a failure? A y equal 1 or a y equals 0? How do I do that? Well, that's where you look at the cutoff probability to make that decision. And then this gets into these ROC curves. What's the purpose of a ROC curve? Why can it be helpful? How do you actually plot an ROC curve? Now, I could actually ask you to plot an ROC curve on the exam. Obviously, you're not going to be able to turn in a plot that's on your computer, but I could have you sketch one. have you, let's say in R, I ask you to do an ROC curve, and then maybe I give you, and then I say, perhaps, why don't you draw it out on your piece, on your paper. And depending upon where you put the curve, that shows me whether or not you actually did it right on the computer. With ROC curves, make sure you have a good understanding of sensitivities, specificities, how to make decisions about which, let's say, model that you're going to go with, depending upon sensitivities or specificities. The area underneath the curve, or hold on, before I say that, I want to make sure that just a second. I'm sorry, now I'm getting into an area that I told you that's not on the exam. So, area underneath the curve is not on the exam. Also, deciding between two different models is not on the exam either. So, it's up to page 35. Because unfortunately, I had not changed my my notes here about where I decide my cutoff part of the lecture notes should be for this exam. Okay, so that's all I have to say specifically about the exam. Do you guys have any questions? I don't know, what's the rule for the number of minutes I'm supposed to wait before I say, okay, that's it for today? Yeah. We'll say I've waited long enough. I guess there are no questions. Good luck in your studying. please feel free to post questions to the listserv if you have them before the exam. And we'll call it a day.